Okay, so now we're going to look at the what we call the work energy principle. Okay, so before we look at this, I want to set the scene. So as an example, let's say I have a car, right? A very simple diagram of a car, right? And the car's moving forwards. Okay. Now, um, there's going to be, in this case, there's going to be a driving force that moves the car forwards, right? As we've seen before. And then there's going to be friction on the road. That's going to try to oppose it, right? So that's how friction works. If you move forwards, friction will act backwards to oppose it, right? And so there we are. And so we can actually label these as a forward force. Well, the force acting forwards, right? And then a backward force that, well, goes the other way, goes backwards, right? So hopefully with me here. Just a simple example. And so why do I bring this up? We're going to be looking at work again. That we looked at previously. So I'm gonna look at because we've got these two types of forces. We've got a forward force and a backwards force. Both of these forces are going to do work. So they're going to transfer energy onto the car. Okay. The forwards force is going to put energy onto the car to move it forwards. And then the friction or the backward force is going to put energy on the car to slow it down. Okay, so we've got this almost sort of like tug of war situation. One force trying to move it forward, one's trying to move it back. Okay, now the car's obviously moving forwards, so we got these. So we got sort of like, as I said, like one force trying to move it forward, one's trying to move it backwards. Now again, they're both going to do work, right? To move it forward and backwards. So then we can sort of work out an overall work, okay? Which is the difference of these two. So it's going to be the work forwards, take away the work backwards, okay? Hopefully that makes sense. So again, when we got this situation of sort of two forces acting forwards and backwards, as I just done here, if we take away if we take away the work done from the forward force from the work done from the backward force, then we get the overall work at the end. Okay, that makes any sense. Okay, and ultimately, as you can see, the car moves forward. That's because the work done from the driving force moving it forward has to be bigger than in order to overcome the work from the friction to slow it down. Hopefully that made sense, okay? And hopefully with me with this. Now, why do I mention this? Well, this plays into this work energy principle, okay? So, when you can notice here as well, obviously I've now added forces on, okay? And if you recall, when we looked at conservation of energy, here, right, this section here, conservation of energy, no forces must act on an object in order for this to apply. What we've got now are forces acting on the object. We've got a driving force and a friction force. So now the situation's changed. So now there are forces on the object. So now that means energy is not conserved, okay? And so more specifically then, if we then work out then the change in kinetic energy and the change in gravitational energy, right? Again, if we work out the two changes in the total change of energy, what that turns out is now if we include forces, it equals the overall work done from all the forces. So it actually turns out it equals the overall work. Okay. Right, and so this is the work energy principle, because again it links energy, as you can see here, changes in the energies has to equal the work. Okay, right, and so these two formulas here we're going to use to look at some problems. I've got this question here first. So here we're told a van of mass 2,000 kilograms starts from rest. After travelling 400 meters, the speed is 12. Constant resistance of 500 newtons acts on the van. Calculate the driving force. Okay, so before we do anything, let's firstly draw the situation. So I've got a van that's probably on the road, right? The van has mass 2,000. Okay, now I'm told it starts from rest, so it starts with 0 speed, let's say over here, and then it reaches a speed of 12. Okay, so that's my speeds. Then as for the forces, well, I'm told there's going to be a driving force, so that's going to act forward, right? That's where my driving force is. And then there's going to be a resistance force which acts the other way, and so that's going to be 500 newtons, right? So hopefully happy with that, right? So it's kind of like friction, right? But that's my force there. Hopefully happy with that. So I'm going to have to use the work energy principle here, because effectively there are forces involved. So that's going to be work involved, right? Because forces have work. So remember the energy principle, the work energy principle says that the change in kinetic energy add the change in gravitational energy, GPE, has to equal the overall work. Okay, so if I work all these out bit by bit, so firstly the change in kinetic energy, well, remember that's always going to be the kinetic energy after, take away the kinetic energy before. So in this case, kinetic energy after, well, the speed is 12, so it's going to be half times the mass, which is 2,000, times by 12 there. Then I'm going to take away by the initial kinetic energy, but initially there's no speed, so there we are. So we work all that out, that's going to be uh, 144,000 joules there. Okay, then the change in gravitational energy, well, remember that's mgh, so that's going to be 2,000 for the mass times 9.8 for g. But hang on, what's the height? Well, there's no vertical height because it's not gone up or down, right? That will be my vertical height, but because it's on some sort of flat horizontal road, it's not going up or down, so overall there's no height, so it just goes to 0, right? And then lastly, the overall work, well, I said that's the work forwards, take away the work backwards. So what does that mean here? Okay, well, I'm talking about the forwards and the backwards force. So obviously the van is moving forwards, so this is my forwards force D, and I'm told the distance is 400. Okay, so the work of the forwards force is going to be D times 400, because remember work is force times distance. So it's going to be D times 400 for that for the work forwards. Okay. Then the work backwards, very similarly, right? This is my backwards force, so the work done is going to be 500 times the distance of 400. Okay, so 500 times 400 there. So hopefully happy with that. And so this simplifies to 400D, take away 200,000. Okay, and there we are. So now hopefully happy with that, so therefore I can substitute it into my work energy principle formula here. So the change in kinetic energy is 144,000 plus 0 for the change in gravitational energy. It's going to be the overall work of 400D, take away 200,000. Then you can see I can work out D quite nicely if I just solve this equation. So I'm I'm going to get D to be 344,000. Then I divide by 400 to get my driving force D to be 860 newtons. Okay, so then we've got this question here. So here I'm told a box of mass 3 kilograms is projected from point A across a rough floor with speed 6. The box moves in a straight line across the floor and comes to rest at point B. The coefficient of friction is 0.4. I'll make a note of that. So mu, the coefficient of friction is 0.4. Work out the kinetic energy lost. Okay, so again, if I just draw the situation on first. So I've got a sort of flat surface, a flat line like this. Then I've got my box, the mass is 3. Okay, I'm also told some speeds. I'm told it is projected from point A with speed 6. So initially the speed is 6. And then at point B, it then comes to rest. So again, that means the speed goes to 0. So it stops moving, okay? Right. I think that's everything I'm really told. I'm not going to consider. We know there's going to be friction. Well, it mentions it, coefficient of friction. So again, that's going to go opposite. It's going to go backwards. I'll call that F for friction. There's not going to be a force forwards. Okay, no force forwards. You might be a tad bit confused about the language here about projected. That doesn't mean there's a force. That means you can kind of imagine it as like kicking it. So if you imagine a kick, initially it's given some force to move it forward, right? Like a kick, like a football. But then it'll slow down because there's no consistent force moving it forward, right? So there's no force forwards, okay, essentially. So that's pretty much everything I can for now. So it's asking me to calculate the kinetic energy lost. So the change in kinetic energy, because that's effectively what it's asking me to do. Work out the energy lost, work out the change in it. But the change in kinetic energy, well, we know the final speed is 0, so it's going to be half lots of 3 for the mass, 0 squared. That will go to 0. Take away the initial kinetic energy, which is speed 6, so a half of 3 times 6 squared. We work that out. That's going to be minus 54. Again, it's going to be a negative because it's lost the kinetic energy, so it's a negative change. So therefore, loss in kinetic energy is simply 54 joules. Okay, and there we are. And again, that's because the speeds have gone down. Okay, and so then in part B, then it's asking again, very similarly, to write down the work done against friction. Okay, so again, if we was to just use the standard formula we saw previously, the work done by friction or against friction, whatever, for almost pretty much the same, really, computationally. So the work done by the friction force, okay. Work done by F, the friction force, that's going to be the force times distance, well, it's going to be F times the distance, which is, they've not told me that actually. So we don't know either, which is very, very unhelpful. So we obviously can't proceed by using the formula. So to work out the work done, we then need to consider the work energy principle instead. So again, the work energy principle is that the changes in both the kinetic and the GPE has to equal the overall work. Okay. Well, of course, the change in kinetic energy, again, it's minus 54. The change is negative. Okay, negative 54. And then obviously there's no GPE here because it's always on the floor, so no change there. and then the work, and then that's going to equal the overall work, right? Now, the overall work, again, the overall work is going to be the work done forwards. I'll include it here. Work work forwards, take away the work backwards. So the work done by forward force, take away the work done by the backwards force. Okay. Okay, now of course there is no forward force. Okay, so that's going to be 0. And then minus the work backwards, that's going to equal minus 54, right? But then very simply then we therefore get the work backwards is just 54 joules then, right? The negatives cancel. And so therefore, because the backwards force is indeed the friction, the work done by friction is this backwards. So work done by friction is 54 joules. Okay. And so there we are. Okay. Then in part C, then it's asking me to calculate the distance AB. So in other words, it starts at point A and ends at point B. So in other words, it wants the distance travelled. Okay. Okay. So that's going to link into this work done formula, the force times distance, right? Because now we know what the work done is by the friction. Okay. So work done by friction by F is again force times distance. We know that the work done is 54. That's going to equal force times distance. So I'm going to need, if I want to work at the distance, I'm going to need to find the force F. Okay. Now, we know what the coefficient of friction is. We also know that the formula involving that is F equals mu R, right? So that means F is going to be, well, mu is 0.4. Friction is 0.4 lots of R, the reaction force. I'll add that on. Okay. There. If I squeeze it in, the reaction force. Then I've got a weight. Now the weight is going to be, again, 3 times G, or 3 times 9.8. Mass times G. And that will get me 29.4. So 29.4 newtons. So then again, if I then look at the upwards and downwards force, resolving that, well, the upward force is the reaction, take away the downward force of 29.4. Again, that's going to equal mass times acceleration, but there is no acceleration up and down, so it equals 0. So very simply, R is 29.4. So therefore, I can now find friction. So that means friction is 0.4 times 29.4, which will get me 11.76 newtons. Okay? Okay, so we're nearly there. So now we can look at this formula again. I say that 54. In fact, I'll get rid of this now. That 54 is equal to F, which is 11.76 times D. Therefore, D, the distance is 54 divided by 11.76, which gets me 4.59 meters to 2 decimal places. And there we are. That's the distance from the 2 points. Okay. Cool. Okay. So we're going to look at an exam question before we look at the last part. Okay. So here we're told a stone of mass 0.5 kilograms is projected vertically upwards with speed u from a point A. The point A is 2.5 meters above horizontal ground. Speed of the stone as it hits the ground is 25 meters per second, and blah, 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 so waffle, right? So it says in part A to use the model and the principle of conservation of mechanical energy. So conservation of energy, just in fancy language, to find the value of this U here. Okay. So it's very wordy, but in essence, it's the situation isn't that complicated, and it's actually telling us what to use conservation of energy. It's quite nice. Okay, so what's happening is we have this stone that's shot upwards, okay, projected or kicked upwards, if you will, whatever, right? It moves upwards. So what's happening is we have this little stone here. The speed is u, okay. And I'm also told at this point A, this this point, it's 2.5 meters above ground. So we have a ground, and the height above this ground here is 2.5 meters. Okay, and then I'm told the speed of the stone as it hits the ground is 25. So what's happening is, obviously the stone will move up, and then it'll come back down to the ground. So when it hits the ground, the speed we're told is 25. Okay, and there we are. That's pretty much everything. Okay. And so we know it won't be work energy principle here because there are no forces acting on the stone. Obviously, apart from gravity, but there's no forces we need to consider here. So it's just conservation of energy. Okay, no friction or anything like that. Okay, so conservation of energy. Remember what that says is that the gain in energy is the loss in energy. To conserve it, right? So if we gain any energy, we have to take that back. So we have to lose it as well. Okay, so we know it's kinetic. We know we deal with kinetic energy and potential energy. Which energy are we going to gain, and which one are we going to lose? Okay, well, obviously we don't know the initial speed, but what we do know is the height. We know that we lose height. Okay, because at the end, when we end up on the ground, well, we go down by 2.5 meters, so we lose height. So the loss is going to be from the GPE. So if we calculate the loss in the gravitational energy, that's going to be mgh. Well, we know that the mass is 0.5, and then g is 9.8, and the height, well, we know that is 2.5. Okay, and so if we work that out, that's 12.25. Okay. Now, now we don't need to worry about the sign. It would be a negative because we are losing it, but we already specified it's a loss, so we don't need to care about the sign. We know that the loss in energy is just simply 12.25 joules. Okay. Now, the change in GPE would be negative. 12.25. Remember, the wording is important here. If I'm telling the loss, I already told you it's a loss, right? But the change is a negative change, okay? So that matters, okay? The change in gravitational energy is minus 12.25, but the loss is just 12.25 joules, okay? I know it's a very slight difference, but there we are. Now that's the loss in gravitational energy. So according to this conservation of energy, we need to gain that back in kinetic. So gaining kinetic energy has to be 12.25 as well. But we also know that we also have the two speeds. Well, we know that the initial speed is this u, but we know the final speed is 25. So then we can also say that the gain in kinetic energy, that's going to be a half um, times, well, the final speed, that's going to be, the mass is zero 0.5, so half times 0.5 of 25 all squared. Take away the initial speed, which is u, so it's just going to be half of 0.5 times this u squared. Again, that's going to equal 12.25. Okay, so that's my change or my gain in kinetic energy here. Okay, so we just work all this out, then that's going to be half of 0.5 times 25 all squared. Going to be 156 0.25. Take away then a half times 0.5 is 0.25 u squared equals 12.25. We just solved this for you now, right? So it's a simple equation to solve. So 0.25 u squared, that's going to be 156. Take away the 12.25. That's going to get me 144. Okay. Then if I divide that by 0.25, I get 576. So therefore, that means u, if I root that, I square root that, I'll get 24. Quite nice. Okay, and that's my u. Okay, and we can confirm our answer makes sense because if u is 24, well, if the speed is 24 and then it ends at 25, indeed, that gives me a gain in kinetic energy, which is what I expect, because the speed has increased from 24 to 25, right? So indeed, we do get a gain in kinetic energy, so that all makes sense. Right. Then part B. So we're told in reality, the stone will be subject to air resistance as it moves from this initial point A to the ground. State how it affects your answer to part A. Okay, so bear in mind what I answered was the value of u. I found the value of u. What this is saying is if we add air resistance and we only change the value of u, right, the start speed, if I only change that, everything else stays the same. Okay, so the heights stay the same and the final speed stays the same. The only thing we're changing to accommodate for air resistance is the value of u. So to allow for that, do we increase or decrease the value of u? Well, when I think about it, air resistance, well, it's a force. So obviously that's going to take some of the energy. Air resistance will try to slow you down naturally, right? So in order to overcome that, you're going to need to increase this speed here, because then that will give greater kinetic energy, right? So hopefully that made sense. So we need to increase u, because air resistance will slow me down and take away some of the energy. So I need to increase the energy, increase the speed to account for that. Okay. So the value of u would increase. Okay. And that's really all they're looking for. Okay. I guess you could say as air resistance. You don't have to, but the idea is air resistance would slow you down and require energy to overcome, right? And so there we are. Okay. Quite a weird question. You get those in normal maths as well, but that's the idea. Okay, now we're told the ground is soft and the stone sinks a vertical distance d into the ground. The resistive force on the stone by the ground is modelled as a constant force of 2000 newtons. And now we're told to use the work energy principle, which is different to the conservation of energy, which we just used. Find the value of D. Okay, so if I sort of draw this situation now, so we've got a sort of slightly different situation. So what's happening is this stone is going through the ground. So I'm guessing it's some sort of mud or something. So it's it's d centimeters above ground into the ground, right? Okay. Um. So say this is my ground. We start here and then we end D. Okay, my distance, my height, which is actually called D. Okay. I picked up the units. It's in centimeters. That's an issue. Okay, because it has to be in meters. But we'll deal with that as it comes. But that's in centimeters for now. Always pay attention to units. But there we are. Okay, so uh, uh, we know that the speed going into the ground is 25, so that's sort of my initial speed now, 25. So that's when it hits the ground, but then after it goes underneath the ground by d, right? Then has some other speed v. Okay. Um. Actually, no. We know no after it sinks. So eventually it'll go to zero speed. Actually, so we know the speed at the end is zero. Okay, and it slows down. It goes. It comes. It slows and stops there. Okay. Right. And that's really everything. But what we need to use the work energy principle because now there's a force added on. We've got this resistance force of 2000 newtons, okay? We need to bear that in mind. So it tells us to use the work energy principle. So that's going to mean that the change in kinetic energy, add change in gravitational energy has to equal the overall work, okay? Now, let's work out the changes in these two energies. So firstly, changing kinetic energy. Okay, well, we know at the end, the speed is zero, so it's going to be zero take away half mv squared. Speed at the start is 25, so half times the mass of 0.5, I believe. Yes, times 25 squared. That's going to be 150 minus 156.25. And again, it's negative because you lose kinetic energy. Okay, I'll make a note it's a loss. Okay, but I do need to keep the sign. Okay, the negative. Okay, then the change in GPE. Okay, well, it's a bit of a funny one. This is because obviously it starts on the ground, but actually we go underneath. So technically, this is sort of my ground level now, if you will. So the change in the change in gravitational energy, well, that's mgh. So the mass is 0.5, g is 9.8, and the height, well, we've gone down by d. Now this has to be in meters. So remember that if well, you should know 1 meter is 100 centimeters. So to convert to 1 meter. Centimeters, sorry, it's 0.01 meters if you divide by 100, right? The units matter because it has to be in meters. So that's simply going to be 0.01 d, lots of meters. Okay, so the height in meters is 0.01 lots of d. Okay, because it has to be in meters. So hopefully that made sense. The units do matter, has to be in meters. So it's not d we've gone down by, it's 0.01 d. That's what we're going to use. And it's going to be a negative because we've gone down by that amount. Okay, so the change in GPE is going to be negative 0.049d. Okay. Um. So therefore, if I substitute that into my work energy formula here, that's going to mean that minus 156.25 minus 0.049d has to give me the overall work, okay? And so the overall work then, again, overall work is the work forward minus the work backwards. Now, there is no forward force. We're only told here there's a resistive force, so resistance, so it's going to oppose it, so it's going to go work backwards. So there's no work forwards because there's no forwards force moving the stone forwards. So work forwards minus work backwards. That's the overall work done. So that's going to be 0. And then the work backwards, well, we do have a resistive force, so that's backwards. So that's going to be force times distance. So the resistive force is 2000 newtons. And again, the distance, well, that's going to be the same 0.01 d. Okay. And that's going to equal minus 156.25 minus 0.049 d equals 0 take away 2000 lots of 0.01 d. Now we just get an equation to solve for d. Okay, so if I simplify this, okay, now I just solve this for d. I get 19.951 d has to equal 156.25. Therefore, d is going to be 7.83 to 2 decimal places. And there we are. That is the value of D there. Oh, to three significant figures. Oh, that's the same thing. Three significant figures. There we are. Cool. So there we are.